Change data capture. So we are covering change data capture today. Um, have you heard of change data capture? Change data capture is quite, and the name itself is quite nice. So capturing the change in data, something like this. So CDC is a set of software design patterns used to identify and track changes in a database. So where is this data stored in database? So whenever there are changes in a data, we identify and track the changes. These changes include what? What are the changes you can see? You can see in a database: inserts, um, updates, or deletes. Inserts, update, deletes changes like this um, can be identified and tracked using a set of software design patterns. That is CDC. And CDC allows applications to respond to these changes in real time, making it an essential component for data integration, replication, synchronization. Quite self-explanatory here as well. So once you are able to capture the changes in a database, we can use it for data integration, integration, data integration. So let's suppose you are getting data in one place, but you have to get that data integrated in another system. So that's the integration. Similarly, replication, what replication is, and synchronization. What is the importance of change data capture? So first importance they're saying is, by the way, I got this from an engineering blog on change data capture at Pinterest. So moving on, real-time data processing, fraud detection, recommendation system. So in fraud detection system, it is quite important that the frauds are detected as soon as possible. Let's say a card is being used, that's a fraudulent transaction, or any other transaction, or any other financial systems. Basically, it's quite important. So whenever there is a fraud, real-time data processing is very important in this case for fraud detection to happen as soon as possible. And similarly, recommendation system, if you are watching a video, then your next video should be recommended based on what you currently watched and how much you showed interest here. So that's also real-time data processing. That's one of the areas of CDC usage. Secondly, data integration across systems, which we briefly talked about here. And then reduced load on source system, only changes captured, not full load every time. So let's say this is the source system and this is my system. In this case, instead of loading the full data every time, you can just get the incremental changes. For example, this could be any system. Imagine there are hundreds or thousands of devices here which are sending some. Let's say this is one of those fitness watches. Okay, so these are giving giving data to this system, and the data aggregation is happening here. Once the data aggregation has happened here, let's say this is another system which wants to use those data for some some dashboard graphs or anything. So and this has a separate database of its own. So but this needs to remain synced with the source system. In this case, you will not load the whole source data every time to my sys. Correct? You will get the changes in the data. Let's say you are running batch jobs to have the sync at 9 p.m. Every day. Okay, so you'll not have the full data load at 9 p.m. every day. Rather, if you are running 9 p.m. At 9 p.m. today, you will get the data, incremental data, after 9 p.m. yesterday. Correct? So that's so reduced load. Hence, if you are only capturing the changes, incremental changes in this case, not loading full data every time, that's reduced load on source system. Again, fourth is audit and compliance. So all the since you are capturing all the changes in a database, insert, update, delete, that can also be used for audit and compliance, from probably logs of these changes. What are the examples we see? um, systems or tools which help us in change data capture today. So two such tools are there. First is Red Hat Debian, second is Apache Maxwell. So this solution, which I was reading from this engineering blog, Change Data Capture at Pinterest, is using Red Hat Debian. Okay, moving on. So Pinterest implementation of generic CDC based on Red Hat Debian. So they're saying that prior to this, they built a generic change data capture CDC, but before building that, they had isolated CDC implementations. But issues were inconsistency, reliability, and ownership issues with isolated CDC implementations. Then they moved on to creating a generic CDC implementation using a Red Hat Debian. And what are the benefits from there? Ensure reliable, low latency, scalable systems with guarantees of at least once processing. Each change in data is captured at least once, so no changes are lost. Support highly distributed database setup. So as you would imagine, Pinterest handles huge amount of data, more than I think in the range of petabytes. So the database setup, as you can imagine, would be highly distributed. So this implementation is able to support highly distributed database setup, implement robust load balancing, and minimize their impact on upstream databases. Um, yeah, so this is the upstream databases. For example, upstream databases is where you are getting the changes. So minimizing the impact on upstream databases and implement robust load balancing. Provide configurability and advanced monitoring integration for users. This is again if you have the changes like we talked about in audit and compliance, you can provide configurability and advanced monitoring from the changes you got for those users. This is the architecture they are following. I'll talk a little more about this, but in short, what is this? They have a control plane, they have data plane. Control plane is reading from Zookeeper configurations, and then uses Kafka Connect API. They are in data plane, they are connecting to multiple shards. So let's say they have some thousands of, let's say, shards, because you can imagine that all the data will not be in a single instance, correct? um, Given the hugeness of data that Pinterest handles, so definitely there are shards, and each shard has a connector connected to it, and they eventually um, when they capture the changes in data, they push that on topics on Kafka, uh, which is a messaging queue, and there are consumers who read from the topics they're interested in. So I hope that makes sense. We'll start moving ahead. Challenge with open source Debian connector. So before talking about shards, imagine Pinterest, of course, like it has a lot of shards, right? So this connector works well with one shard, but Pinterest has distributed database consisting of many shards. So that was the challenge. What was the solution? They first thought of changing the implementation of Debian connector, but in that case, if they upgraded to future versions of Debian, that would be difficult. And same issue was with Apache Maxwell as well. So what do we do? Second way is separation of control and data plane, which is the architecture I just showed you here. This is the architecture they are using. Now let's start talking about the control plane. So control plane, data plane, two parts. Let's talk about control plane. So control plane consists of a single host with auto provisioning. Um, so Here we're talking here we have single host with auto provisioning. They're using AWS for this single host, and that means if this goes down, it auto provisions it back. Maintaining that one host in control plane, and that single host runs main logic every minute. And what is the main logic? I'll talk here, but it runs a main logic every minute, and it also emits events for monitoring. So what is the main logic? So in main logic part, it reads the connector configuration and Apache Zookeeper. So here connector configuration. So there are some connector configurations. So it reads the connector configuration and Zookeeper, and which contains information about the database topology. This combined information represents the ideal state of the system, including the number of connectors that should be running and the updated configuration for each connector. Okay, so pretty much number of connectors that should be running and the updated configuration for each connector. This is the ideal state of the system. Now it calls the data plane Apache Kafka Connect API, calls the what? Kafka Connect API here, to obtain information about the current state of the system. So it has ideal state. It is trying to get information about the current state of the system, such as the status of currently running connectors and their configurations. Remember, it has ideal state, which includes number of connectors and that should be running and the updated configuration for each connector. It calls Kafka Connect API to obtain information about current state of the system, which again has running connectors and their configuration, compares the ideal state and the current state, eventually comparing running connector and configurations, and takes action to bring the current state closer to the ideal state. For example, it creates new connectors for new shards, updates the configuration of existing connectors when necessary, and attempts to fix failed connectors. Got it? So let's say 9 connectors were running, but ideally it should have 10 connectors. It can create new connectors for new shards, updates the configuration of existing connectors. Connector number 3, let's say configuration update is required, so that it updates as well and attempts to fix failed connectors. Got it? Okay, so this is the main logic which runs every minute in that single host that is in control plane. And that single host, if it goes down by for some reason, it uses AWS instance, and it has auto provisioning here, having both min and max value set to 1, so that it always keeps that one host in this control plane. Even when it goes down, it creates another one. So, and emit events for connecting. So that's control plane. Let's now go to data plane. So data plane, what is data plane? This part. Okay, what do we see here? We have some workers, and they are reading from shards, and they produce data on Kafka topics, and that is consumed by consumers. Pretty much that. Let's read here. So data plane, to ensure even distribution across 3 availability zones. So they're using 3 availability zones. Okay, to ensure even distribution across 3 availability zones, we operate Kafka Connect in distributed mode on a separate cluster with more machines. Okay, Kafka Connect being operated in distributed mode to ensure even distribution across 3 availability zones. This is the Kafka Connect. This is running in where is that? This is Kafka Connect is in distributed mode on a separate cluster to ensure even distribution across 3 availability zones. All hosts in this cluster join the same group and run Kafka Connect in distributed mode. Each host may run multiple division connectors. Okay, so where with each connector responsible for a specific database shard. So as we discussed earlier, division, like it was one division connector was worked well for one shard, so it has multiple division connectors, each connector now responsible for a specific database shard, and those multiple division connectors are running in each host. The primary function of a connector is to capture database changes and send them to Kafka. Exactly like I said here, capture change, send to Kafka, capture change, send to Kafka, capture change, send to Kafka, like this from each shard. Now coming to Kafka. So Kafka stores metadata about connectors in several internal topics that are not exposed to end users, and the actual CDC data is stored in pre-configured topics within Kafka, which can be consumed by users. So some internal topics and some topics which can be consumed by users. Now, internally, Kafka Connect utilizes a select group of Kafka brokers to facilitate a distributed computing framework. This includes tasks like leader election and coordination. Brokers, brokers are the machines in this case. So this we talk about group here as well. Just what I was just trying to look for. All hosts in this cluster join the same group, uh, which is a group of Kafka brokers. So now talking about, so that's the architecture. Hope this was clear. We talked about what is CDC, what is its importance, some examples of CDC tools in market. I think both are open source, and then Pinterest implementation of isolated the CDC and its issues, then generic CDC implementation, or what are the benefits, architecture that they followed, and in architecture, and we discussed the architecture here: control plane, data plane, Kafka, and the main logic and control plane. Now some challenges that they faced. So first is high QPS, which is expected in a big scale that Pinterest works with. So in this case, they were facing out of memory error in CDC tasks, which would be I guess here. It's a small article, so it was not very vividly clear, but I would guess CDC tasks would be these. So it's saying out of memory error in CDC tasks. So solution was rate limiting and starting tasks from latest offset. Second is rebalancing timeout. So in this case, they were seeing some issues like all connectors were assigned to single host, leading to high latency. In this case, the solution was to increase the timeout, rebalance timeout configuration. And okay, talking a little bit more about this, the primary source of this issue is that default heartbeat timeout value, which is too brief. As a result, the framework does not wait long enough before reassigning tasks to other workers. So it says it deploys in Kiwi store. So store clusters could take 2+ hours, causing 2+ hour leader failovers. Tasks failed with outdated leaders, prompting the control plane to delete and recreate them, triggering constant rebalancing over 2+ hours. Solution was to allow CDC workers to handle shard discovery and failover, which reduced failover recovery latency to sub-minute and minimized rebalances. This is I did not write it here because this is more like reading from here, but I hope what I covered here is pretty clear. And similarly, there are some duplicate task issues, and solution was version upgrade and increasing the balance time out to 10 minutes. And then there are some graphs that they had given. Okay. And okay, so clearly there are CPU percentage improvement, task status breakdown by worker cluster improvement, and number of hosts each task and so on, that is improved. So basically here we see that each task runs on only one host, and prior to this it was running on so many hosts. So this is 3 0 to 3, like that. So I think each task was running on multiple hosts, which was one issue. After solving it, it is running exactly on one host, and CPU percentage remains at 40%. But before that, it was touching 100 as well in many cases. So cool. That's about it, I would say. And in next steps, they have mentioned that they want to enhance scalability. They want to implement robust disaster recovery measures, by replicating data across different regions, and again near real-time data ingestion. So they are trying to develop real-time database ingestion system utilizing CDC to ensure timely data accessibility and efficient decision making. I hope these all made sense, and thanks.